In this video, I'm going to introduce you to stress and strain diagram. Yeah, stress strain curve. It shows the relationship between stress and strain, and as we already know, that it can be obtained by applying loading to a test coupon, and then we measure the deformation. So, study of a relationship between stresses and strain in material, it is very important. Ability of the materials to withstand the loading that imposed upon it and the resulting deformation. It all depends on the stress strain characteristic. Just a quick review. I think we have covered this in our previous lecture. If you still remember, the definition of stress is the force intensity per unit area, and also we have a strain here that can be defined as the change in length compared to the original length. So here in this slide we have an example of a stress strain diagram. Yeah. So from the figure here, we can see that the slope of this linear segment it corresponds to the modulus of elasticity E, and we can see that the greater the modulus, the stiffer the material, or the smaller the elastic strain when stress is applied. Yeah, and in this figure, if I ask you to guess which one is more stiffer, whether the left one or the right one, if you can recall what we have learned beforehand, the stiffness of material is indicated by the modulus of elasticity. That is the symbol E or Young modulus, and the stiffness is, as we can see here, the stiffness is seen from the slope of the graph of stress versus strain. And if you can guess which one is stiffer between these two graphs here, we can say that the left graph material is stiffer because the slope is much higher compared to the right one, and we can conclude that materials that exhibit this type of stress strain diagram is more stiffer than the right one. So almost all of mechanical property of material can be obtained from the stress strain diagram, with the only exception is a Poisson ratio. But for Poisson ratio, we can determine by knowing the change in cross-sectional area of the specimen at a point along the elastic region of the stress strain curve. And from the stress strain curve, among the information that we can obtain include the modulus of elasticity, the proportional limit, elastic limit, the yield point, yield strength, and also the yield stress, and also the tensile stress of that particular material. So we know that a stress strain curve is the behavior of material when it is subjected to loading, and from the graph here we have stresses that are plotted along the vertical axis, and as a result of the stress that we applied, we have a corresponding strain that are plotted along the horizontal axis. This is the figure of characteristic that shows the characteristic of stress strain of a diagram steel that is commonly used material for structural members and also mechanical element. And here in this region, we can see that there is a straight line. We can see that there is a straight line that shows elastic behavior with stress that we can say directly related to the strain. And as you can see in the figure here, the proportional limit is the point where the stress and strain are directly related. The stress at this point is called as a proportional limit stress, and beyond the proportional limit is the elastic limit, and up to this point the material will remain perfectly elastic. If load is taken before this so-called limit, the material it will certainly goes back to its original shape. And this is the thing that we have to remember for this phase within the elastic behavior or elastic region. If the loading is removed before it reaches the elastic limit, for sure the specimen will return to its original shape. And next we move on beyond the elastic limit. After the elastic limit, a yield stress will occur. The material will extend rapidly with a minimal loading increase. And here we can see that the material will deform permanently, or what we call as a yielding. And we can see a plastic deformation. And here, in this phase, material will undergoes a permanent deformation, also called yielding or a plastic deformation. And we have to remember within this phase, once a yield point has been reached, a specimen continues to elongate or strain without any increase in loading. And this phase, the material is referred to as being perfectly plastic. And now we have reached an ultimate stress point. That is the material maximum strength before it will fracture or breaking. And this corresponds to the peak on the stress strain curve here. And at this stage, there is a buildup or accumulation of dislocation, and grain will begin to align. Yeah, the grain are the individual crystal that make up a polycrystalline material, and when a material is subjected to tensile loading, the grain can begin to align themselves in the direction of the loading. Yeah, right. So strain hardening is the ultimate strength, while specimen is elongating. Its X sectional area will decrease, and decrease in area is fairly uniform over the entire gauge length. And within this area, like what I have mentioned before, we have a two-way many dislocation, and there is no more room left for dislocation. And also within this phase or within this region, we can see that all grain will start to line up. And now we move on to our last phase within the stress strain diagram. And here we have what we call, there is a breaking point where the material strength will fail. And the stress at this point is what we call as a rupture strength. And here we have the cross-sectional area will be locally reduced, and this will leading to a necking, as we can see on the specimen. And here we can see the necking happening as the specimen stretch more. And here we can say that the specimen will finally break at the fracture stress. And now let's recap what we have learned so far. We know that the stress strain curve, it has two main parts, like what we can see in the figure here. We have an elastic or linear region, and we have a plastic region. In the elastic region, the curve is straight, and it indicates the strain will increase directly with the strain. And we have Hooke's law that describe this linear relationship, and the ratio of stress to the strain is what we call as a Young modulus. Yeah, a Young modulus is also called the modulus of elasticity, or also stiffness, and it measures how much stress will occur due to the given, how much strain will occur due to the given stress. And because strain is dimensionless, Young modulus has the unit of stress or pressure. And we know that different materials can have quite different values of a Young modulus. For example, for anisotrophic materials like wood or composites such as a carbon fiber, the value of a Young modulus will depend on the direction in which the loading is applied. And From the graph here, we have Young modulus for different types of material. We have titanium carbide, we have carbon steel, we have aluminum, and also we have polypropylene. This indicates the range of a typical Young modulus values for polymer, metals, and ceramic based on the information that we can see here. From the stiffness, we can say that in general, ceramic have a higher values of Young modulus as indicated by the higher stiffness value from the graph here. Metals have a slightly lower values compared to ceramic, and polymers in general have a much lower values compared to ceramic and metal. So if we look at the figure here, why is Young modulus different for different types of material? Yeah, so we need to understand what happened at a molecular level. We know that on atomic level, a material's Young modulus is closely related to the strength of the bond between its atom. As you can see here, polymer, it has a very low value of Young modulus compared to ceramic and metal, because polymers, they are held together by primary bonding, covalent bond, and secondary bonding, that is van der Waals and also hydrogen bonding. On the other hand, metals such as aluminum, they are held together by metallic bonding, and ceramic is held together by covalent bonding and also ionic bonding. And I think we already discussed about Hooke's law in our previous lecture. So most engineering materials exhibit the linear relationship between stress and strain within the elastic region. And Hooke's law, it is discovered by Robert Hooke in 1676 using spring, and it is known as Hooke's law. And this is the equation of Hooke's law, where the E represent the constant of proportionality, also called the modulus of elasticity or Young modulus. So in simpler terms, we can describe Hooke's law as how much a material will deform or strain when a specific force or stress is applied. And this behavior can be consistent and predictable up to a certain point within that we call as the elastic limit in the stress and strain diagram. So most grades of steel have quite the same value of modulus of elasticity. Most steel types have the MOE value equals to 200 gigapascal. If you can still recall how do we define a modulus? We can define modulus as mechanical property that indicates the stiffness of material. So it measures elastic deformation. The higher the value of a modulus, meaning that the material is more stiff. And if the value of E is larger, meaning that it has a greater resistance to deformation. So as a comparison, steel has a high modulus value. On the other hand, materials such as vulcanized rubber has a low modulus value. And from the graph here, we can see that different type of steel. We can see here we have soft steel, we have structural steel, machine steel, hard steel, and spring steel. And this shows the stress versus strain for different steel grade. And from the slope here, it indicates the modulus of the steel. So now we're going to talk a bit about the yield strength. So in engineering stress strain curve at 0.2% strain, a straight line is drawn parallel to the elastic curve, which follows the Hooke's law. So this is called as the 0.2 offset method. It is the method that used when the exact point is hard to identify, like what we can see in the figure here. We can see that the exact yield point for this stress strain graph is quite hard to identify. So what we do, a line is drawn parallel to the elastic path, starting at 0.2% strain or elongation, and then we have the intersection of this line with the curve that define the yield point. Yeah. So if we compare this stress and strain graph, if we compare this with this one, we can see that for this stress strain graph, the yield point is quite difficult to hit. It is not clearly defined. But this one, we can easily identify, we can easily determine the yield point here. So why do we choose 0.2%? Yeah, because it is a standard convention in engineering, and 0.2% is commonly used arbitrarily defined number used by the engineering community, and we want to ensure consistent and objective determination of yield strength. And this is especially helpful for materials with unclear yield point, like what we can see in the graph here.